we are starting with Mesut Durukal. Mesut has an experience from agile software testing projects and is acting as a product owner and end-to-end test automation leader. Mesut is now going to talk about artificial intelligence assistant. And since I talk quite a lot, Mesut, over to you.
Thanks, Thomas. Thank you so much. And let me share my screen. Okay, I think we're ready. So, hello and welcome everyone. I'm very happy to be here in this amazing conference, Tesena. This year, this is my second attendance to Tesena because the first one is in March in Vienna. And it was my last physical conference attendance because nowadays we are not able to meet face to face, but at least we could make it this way online. So I'm very happy to be here again. And in this session, we are going to talk about some practical applications of machine learning in different software testing stages. But before deep diving into the subject, let me briefly introduce myself. My name is Mesut and I'm from Turkey. I'm a QA engineer with more than 12 years experience. And mostly I worked in Istanbul. I was working for Siemens until last month for 4 years. And this month I moved to Japan, Tokyo, and I've started to work for Rapid Robotics, but I haven't gone to the office yet because still I'm in self-quarantine, but next week I will start going to the office as well. And here you can find some contact information for me, so please do not hesitate to reach out to me or just feel free to contact me. And this is the brief agenda for this talk. As I told in the beginning, we will cover some different adaptations of machine learning in different software testing stages. And we will try to do this in a systematical manner, starting from the first stage until the end of the life cycle in an ordinary software testing project. But firstly, before that, we will make a quick reminder to quickly remember the working principles or the underlying working principles and the mentality for the machine learning algorithms or the teaching processes. And finally, at the end, I will share a case study in which I try to classify the bugs into different severity classes via reading their summaries and description texts. So let's start with the introduction section. Firstly, let's start by discussing why are we talking about this? I mean, why are we discussing or searching for different adaptations of machine learning into software testing stages? Because as software testers, we are not data scientists or machine learning practitioners, but still should we be involved in this area? I think we are searching for different adaptations because we have some challenges and we are trying to cope with them. Because nowadays everyone is trying to be the first in the market. There's a great rivalry and we have a very limited time to test our products. We have a very complex and complicated structure to be verified, and we have a very limited time. Sometimes personally, I remember that I had only 1 hour testing window before going production. So to verify this dense context, because technology is growing too fast and everyone is integrating their product to different applications of different platforms. So it's very tricky to cover all this context in a very limited time. And we are working in an agile environment, right? Everyone is trying or everyone is changing or updating too fast. Sometimes I start work to verify some features, and then I learned that the feature is updated or changed already by the developers or by the owners of the product. So sometimes we feel really desperate and we feel that we need some help or we need some support from someone or from some platforms. So at this moment, can we get some help from the machines or machine learning algorithms? Let's discuss this. Yeah, we know that machines are designed, developed, or created by the human being, so they have already some limited capacity in some manners. But they have some certain advantages as well. For example, they don't get tired, right? Or they don't forget. If we put an information into a machine, then it is always there unless we delete it. Or they don't get tired. I mean, at the end of a long working day, it's very possible for me as a human being to overlook some bugs or some vulnerabilities in the product because I'm already tired at the end of a long working day. I already want to go to home and my motivation goes down. And it is very likely for me to miss some bugs. But for machines, it is not the case. And if we need some resources, then we can immediately create some additional resources, create some additional virtual machines. But when we need some extra colleagues or some extra headcounts in the project, it is not that easy. It requires some adaptation time. After we add some extra colleagues in the team, then they cannot start immediately perform. But for the machines, it is not the case. So it is in our hands to make use of these advantages. We can utilize the advantages and benefits of the machine learning algorithms, because machines can overperform human beings in some manners. They have a very high capacity to analyze a large variety of data. For example, when you put in front of me 1,000 bugs, then it is not easy for me to analyze all of them. 1,000 bugs, each of them separately. But a machine or an algorithm can analyze all of them in a very limited time, very short time. And this is just an example from the match between the champion of the game and the machine learning machine algorithm for Go game. It's a very complex game, much more complex than chess. And the champion was not expecting this result, but the result was really surprising and maybe disappointing for the ex-champion, because we know that they can or the machine or the algorithm can learn all the alternative paths, or can imagine all the patterns, the possible patterns. It has a very high capacity to do that, or capability to analyze that. And we see that in our daily lives. A lot of machine learning algorithms are used, right? We encounter them in our daily lives. For example, when I'm responding to one of the emails in my box, I start with the greeting. I say hi, and I see that it is completed with the name of the sender. And when I see that, I'm happy, right? Because it makes life easier for me. I do not bother myself to complete it manually. So the algorithm completes it in the name of me, because it knows how I can complete the rest, and it works very consistently. Because how does it know that? How does it know that I will continue with the name of the sender? Because it's observed all the past experiences and all the past patterns in my or for me or for the other users, for the other email users. In most of the case, they start with the greeting and they continue with the name of the sender. It is the ordinary pattern. So after the machine knows or learns this ordinary pattern, then it makes the feature estimation or feature prediction. And it suggests me the best or the most likely feature action or reaction. And we will see the applications in the software testing applications as well. But at this point, let's discuss about the learning of the meaning. The meaning of the learning, because it is important. The terminology itself is important, because learning itself is something different than memorizing something or being explicitly programmed. It is something different, because not like memorizing something. Even if we encounter a different sample, different from the others that we observed in our past experiences, still we can imagine what it can be, or still we can make some predictions about what it can be, or how it can affect our life or affect our system. For example, if I ask you what the images on the bottom of the slide, you can all imagine, or you can just predict that it is a chair, right? It is not, maybe it is the first time for you to see this image, maybe, but because it is not exactly the same as the others that we observed before, but still we can imagine, right? This is the meaning of the learning, because we learned how it works, and we've learned the working principle of what a chair is and for what it stands. Because a chair, the functionality of a chair, we all know that we can sit on the chair, and yes, still it is not like a traditional chair with 4 legs, but still we can know that we can sit on this image. So it is a couch or a chair, whatever it is, but we know that how we can use it. And it is not a very niche area actually, because some researchers are working on this, working heavily on this area since 1980s. Because Alan Turing at that time had the courage to ask these kind of questions: if the machines can think, or if the machines can learn. So from that time, too many research are performed, and nowadays we can really see lots of applications in our daily life as well. And in the session, we will go through the adaptations in different software testing stages. But finally, let's go over the background, the working principles. As we see, the data is very important, because when I'm teaching to someone, if I do not provide sufficient data, then I cannot teach what I intend to write, or the guy that I'm teaching to cannot learn what I'm trying to teach him, because I'm not providing sufficient data. So it is the same for the machine learning algorithms. If we do not have sufficient data, then the machines will not cover all the scenarios or all the cases. But if we feed sufficient data, then it will learn the basics of the system and constructs the model. And according to the model, for the upcoming samples, it will predict the related reactions, and it will observe the reactions on the system. So it is again very similar to our biological learning as human beings. For example, as a software tester, if you come to me and ask to test your system, my response would be, yes, I can test your system as a software tester. But first of all, please teach your system to me, because first of all, I have to know how, or I have to learn how your system works, or supposed to work. Because otherwise, if I don't know the expected responses, the expected results, how can I compare the actual results, right? Yeah, okay, I can try something. I can click the buttons, or I can perform some queries, and I can get some responses. But in order to verify the response itself, I should know how your system should work, and I should know what the expected results are or should be. So let's now go one by one over the stages on which, or by how we can adapt machine learning algorithms into our activities, software testing activities. Because it is a big question. I mean, how we can utilize machine learning in our software testing activities. Let's see each of them one by one with different examples. I will share some different research and some different commercial tools, platforms, so you can regard this as a benchmarking as well, and you can go and check how they work, because I will share some open repositories as well. But first of all, what we will discuss is, starting from the test case definition stage, we will go over the implementation stage, and finally the maintenance stage. We will see examples in each of them. But there is a key point here. There is an input-output relationship in each two consecutive stages. I mean, let's go with an example. Maybe after we analyze the requirements, we design our test cases, right? And we make a traceability between these two, the requirements and the test cases. We build our traceability, and we construct a mapping. There's an input-output relationship. And by analyzing this relationship, we will utilize this traceability. Let's see what kind of applications we can do. I think it will be more clear by going over the examples. First of all, let's start with the test case definition stage. The first thing that we do in our lifecycle is to generate test cases, right? After we generate, we will implement them, to automate them, to integrate them into our CI/CD pipelines, and then we will execute them, and finally we will report the results. But first of all, test case generation. And how can we generate test cases automatically with the help of machine learning or artificial intelligence adaptations? This is an example from the data structure used in an API communication. So it can be seen in the requests or the responses. When you perform a get request, in the response you will see some entities, right? So this is an example from the library API, in which I can query the books, and over the library, when I get the books, I see this kind of data. I see some book entities, And in each entity, I see ISBN number of the books, the price, the year, and some other information and some other fields. And what else I can see is, I can see what kind of data types are used to represent these fields. I mean, maybe a string value is represented or used to represent the ISBN number, or a double value should be used to express the price, or an integer or a float, whatever it is used to express the year information for the book. So I can observe what kind of structure is used for this data. And then what I can do is I can construct some queries, right? For example, I can inject some values inside these fields in the positive or in the negative value, in the negative manner. I mean, maybe intentionally I can inject some string values in the year field just to see what will happen. See, we already generated a negative case by injecting some different values other than it should be. And we will expect the related responses. For example, for a bad format, maybe we will expect 400 response, or for an unauthenticated query, we will expect a 403, or for the positive queries, we will expect 200 responses. So we can generate this kind of queries after we learn and we observe how the structure should be. And for the UI case, apart from the API side, for the UI side, we can generate some test flows via visual recognition. I mean, again, let's go over with a daily example. When I go to online shopping site, I can order something online, right? This is one of the things that we do most in these lockdown days. We are going to online shopping sites, we are ordering something, and it is posted to our house. So even if it is the first time for me to go for a site, I can still use it. I know how to use that site because I know the buttons and the icons on the page. But how can I know that? Because it is the first time for me to use that site, because no one taught me before to use that site. But I have some past experiences. And for most of the case, these sites are working similarly. And when I see a basket image on the page, then I can imagine that it stands for an online shopping cart. And whenever I add some items into the basket, then they are added in it. And in the next page, I can see all the ordered items in the shopping cart. So in this way, I can generate some test flows. I can add items and navigate to the next page and check if the items are there or not. At the end, I can confirm my order, and in this way, I can generate positive and negative test scenarios. So we can generate test cases for API and UI endpoints as well, and interfaces as well. And after we generate our test scenarios, what we do is to implement or to generate our test code. And now we will see alternatives to test code generation in an automatical manner. The first alternative is to detect some callable methods in the class that we want to test and call these methods with the related parameters. With the again, in the positive or negative manner. I mean, we can call the method with a missing parameter, or correct parameters, or with different data ranges of parameters. I mean, if I'm supposed to give an integer value into one of the parameters, then I can send some corner cases like the negative values, the maximum possible value, lots of different range of data. I can call the method in lots of ways, and in this way, I can generate lots of test executions. And apart from that, to generate the algorithms, we can make use of the input-output relationship. For example, on the slide, we see an example. We see a pair of input and output, and for us, maybe it is not very easy to understand or to detect what is the relationship between this input and output. But for a machine or for an algorithm, it is very easy to understand what it is. And let me describe what is required to reach to the output from the given input. Every value in the input is multiplied with 4. And each one of them is sorted from biggest to the negative to the smallest, and the positive values are filtered out. We see only the negative values in the output. So these are the required operations to reach to the expected out from the input. So after detecting these required operations, we can inject the related code, right? It is just injecting the needed code for the related operations. So by using this mentality, we can construct the test code as well to implement our algorithms. And we all know as software testers that sometimes UI or front-end automation is very tricky, right? Because it is not stable. And sometimes sometimes our tests are fragile. They can be broken. Because if we locate the elements on the pages or select the elements on the pages by traditional ways, I mean, if we use the ID of the element or XPath or some CSS path or some other locators for the element recognition on the page, then they can be changed. Sometimes they change, the developers change the ID of the element, they change the XPath because they change the design of the page. And when it is changed, our tests are broken. So it is fragile. But instead of doing this way, we can perform some visual recognitions. So this is a code taken from the open repository from test.ai. So what they do is to pull all the images from the page and to find what we are looking for. They try to match if we are searching for an cart item, then it is tried to be found visually. So in this way, we do not have to worry about the fragile tests anymore, because even if the locators of the elements are changed, then still our code will work in the proper way. And after designing our test cases and implementing them, the next thing we do is to execute them. And for the execution, what can we do? Let's discuss this. And during the executions, we can collect lots of data, right? For example, in my first 10 executions, I can measure all the execution durations. For example, the average execution duration for my first 10 executions was, or were maybe, let's say, 10 seconds. And in the 11th execution, if it is not 10 seconds, it is not 11, 9, or around that, but it is maybe 30 seconds, then I can predict that something is wrong, right? Because in the first 10, it was in average 10 seconds, but now it's 30 seconds. So see, we found an anomaly because from my past experiences and from my past patterns, I was expecting something around 10. Maybe 11, 12 are all acceptable, but if it is 30 seconds, then I can regard this as an anomaly. So I can go and check if there is something wrong. And I can collect lots of similar data. For example, in each execution, maybe I can collect the number of calls to an endpoint for an API. And if there's an anomaly for the number of calls to the endpoint, then I can predict that something is wrong there. Maybe the endpoint is not responding properly in time. So I can go automatically, because in this way, I do not have to go manually each time to check if something is wrong. But in this way, now, whenever the anomaly is detected, then the algorithm can warn me by raising an alarm, and I can go and check if something is really wrong or not. And after all, our last stage for the software testing lifecycle is the maintenance stage. And in maintenance stage, what we do is to refactor our code to improve the quality of the code, or to refactor to remove vulnerabilities in the code, right? And how do we do that? Normally, I develop my code and send to a colleague in the team to review the code. And after she reviews it, she sends it back to me, and I remove vulnerabilities in the code. So sometimes it means a waste of time because I'm sending to her and she's sending again back to me, and this requires a certain time. But instead of doing this, if we can somehow teach the machines what the anti-patterns are, or what the best practices are, then the machine learning algorithm can do it in the name of us, right? For example, how do I do the code review process? I have a checklist. I'm checking lots of items if they are performed in the proper way. If I teach this to the machine, then we can do it in the automatical manner. I mean, if I teach the machine that having some embedded numbers, magical numbers in the code is not a best practice, it's an anti-pattern, then in the next round, if it detects some magical numbers, it can warn me. You told me that this is an anti-pattern, and now I see a magical number in your code. Please go and check and remove it. So we can do that over machine learning algorithms as well, and we can utilize these algorithms in the maintenance stages as well. And for the prioritization of the test cases, we can use it because infinite testing is not possible, right? And our limited testing window and testing duration, sometimes we need a prioritization to firstly execute the most prior ones. And for this purpose, we can again use machine learning algorithms in the different way to serve to our goal in the best way. And finally, what I will share is the adaptations for bug management purposes. And let me describe this over the test, over my case study. It will be more clear with some concrete numbers and results. So I tried to apply this different algorithms to classify our bugs in my project. And in this project, we had 6 different severity levels, starting from severity 1 to severity 6. And severity 1 is the highest one. But severity 1 was the ones which are related to human life issues. For example, if you have a hardware in your project and if there's a current leakage and it can harm the human body or human life, then they are regarded as severity 1. So actually in our project we had no severity 1, but we had 2 to 6. And severity 6 and 5 and 6, those two were regarded as not real bugs, but they were regarded as change requests. So we can think that we had 2, 3, and 4, 3 different severity levels actually in this project. And after I read the summary of the description of a bug, what I will try to do is to imagine if it is severity 2, 3, or 4 to classify into one of these classes. And this is the distribution of the numbers of the samples. Mostly we had some class 2 bugs. And over this distribution, what I get with is the result is something like this. This is a confusion matrix over different algorithms. And the overall accuracy was 73%. It is kind of acceptable, but it can be still improved. And what I found to be improved is it is not a very balanced distribution, right? There's a bias on class 2 samples. So what I did in the next round is combine 3 and 4 together. And now I will imagine if a bug is in class 2 or 3 or 4. Now I will have 2 classes. And does it make sense? Actually, yes, because in our project, class 2 severity 2 bugs are regarded as the release blocker bugs. So now in this way, we will predict if a bug is a release blocker or not. So now the distribution is like this. There's this one is much more balanced in the distribution of the bugs. And this time the confusion matrix is looking like this. And the overall accuracy is 82% accuracy. And this was the results for my case study. And let me finally summarize what we discussed in this session. So we went over lots of different adaptations of machine learning algorithms in different software testing stages, starting from the early stage which is the test case generation stage. Then we continue with the test case implementation stages, how to generate test code automatically. And finally, in the maintenance stage, we discussed what we can do with the help of AI algorithms to refactor our code or to review our code and to manage our bugs. So this was the end of the slide, and I hope everyone enjoyed it, and I hope you get lots of insights. And if there's some questions, I will be more than happy to answer them. I think we have some time to do that. So if there are any questions, I will be happy to answer them. Thank you so much for listening.
Thank you, Mesut. Thank you very much. Actually, there are some questions, so I will start with them. First of all, I think that you can see them, so I would like to show them to you as well.
Okay, let me...
Let me know. Okay, here are they. So, as you can see, first one, what ML-DL models are you using most often, or does it depend fully on what you are testing?
Exactly, it depends on what we are testing, because sometimes, let me give an example. In the case study that I shared, we worked on the bugs. So the bugs are the string values. So they are expressed in some text, written text. But if we are working on the images or the sounds or videos or whatever it is, then we can utilize some different algorithms. But for the bugs, since we are working with string values and text values, then we can use lots of NLP algorithms, natural language processing algorithms. But for the videos, for the images, we can use lots of different algorithms. So it depends on what we are working with or working on. But for my case, for example, I compared the results coming from lots of different implementations. I compared the performance of the SVM algorithm, some other deep learning algorithms, but you can make a benchmark to see the results from different implementations, because machine learning for the important point for the machine learning algorithms is apart from coding, fine tuning. You have to optimize the parameters, so you have to see the results coming from different implementations. So you can see lots of different implementations, and you can decide which one is the best to use in the application.
Okay. Thank you. Okay, let's follow the second one. What do you think is the current level of adoption of AI ML? Is this only or still only for early adopters? What do you think? What's your opinion on that?
I understand from the question, it's a general question, right? You mean the general approach or general situation in the software testing field? I mean,
I would say yes.
Okay. So I see the current situation is I see lots of people are working on this, and sometimes, especially for the visual recognition or visual automation part, I see lots of products are in the market already. So and in the future, I think in the near future, I think we will see lots of them more. So I think it is not a very I cannot say that it is a very early adopter, but not mature as well. But I can say that there's a heavy effort to adopt these principles in software testing activities.
Okay. Thanks a lot. We have two more questions, and I think we still have some time, so let's try to answer both.
Yeah.
What would be the first activity in testing where you would start applying artificial intelligence or machine learning?
Yeah, actually, again, the same question. Sorry, it depends, because we have to analyze the bottleneck in our life cycle. For example, in my life cycle, if I understand that, if I detect that I'm suffering too much on the code merge, okay, let's say code merge is a pain point for me, then I can concentrate on that part. I can analyze the data, or I can analyze the merge durations on the pipelines, and I can try to classify or try to construct a model on the merge on this way. But if my point is something else, for example, if my point is a pain point is to classifying the bugs, then I can concentrate on classifying the bugs. So it depends. So I think personally, we should detect what our bottleneck is, then we can start with that part.
Okay, thank you. Thank you very much. Okay, still two questions. Another one is where you can take valid data for training if bug-free software doesn't exist or hasn't existed yet.
I think it is, even if it is not bug-free, it doesn't mean that it is not valid, because okay, it is not bug-free, but still it is valid for us, I think, because what we are intending to model is construct our model is maybe the real data, so it shouldn't be bug-free. So it is the code in the production environment already, then we can use it, I think. So I think it is still a valid data that we can use.
Okay. And last, but definitely not least, can you please somehow assess the testing efficiency increased by using artificial intelligence?
Yeah, actually, it is not very easy to measure it in the numeric manner. I mean, because we are talking about the reduction of waste of time, right? Because we are talking about the efficiency. So in the traditional approaches, we are trying to perform lots of things manually, or even if we are automating things, but not with the help of machine learning or AI adaptations. Maybe it is not very consistent. I mean, again, let me again give the example from the bug management. When I'm creating a bug, is it, or am I assigning the severity level correctly? I'm not sure. I don't know, because when I'm putting the label with the severity 2, I don't know if it should be really 2 or 3, because I do not have the ability to check all the past bugs, because maybe if I'm saying severity 2 to one of the bugs, maybe another guy in the team can say it should be severity 3. So for me, so for human beings, maybe we are not working in the best way, or maybe working in the maximum performance, or maximum consistency. But for the machines, for a machine, it can really observe all the data up to that point. So in this way, we can remove the consistency and improve the consistency and improve the performance. But in the numeric manner, it is not very easy to say to make a comparison or say some numbers about it.
Okay. Thank you, Mesut. Thank you very much, not only for your presentation, but also for the answers after the presentation. Guys, for everyone else, if you want to talk to Mesut directly, please visit our coffee corner. The link is either on your webpage, where we are streaming this conference, or here on Microsoft Teams in the chat. Mesut is heading there, and once more, Mesut, thank you very much. Thank you.
Yeah, thank you. Thanks for having me. It was a pleasure for me. And yeah, as you told, I will be in the coffee corner. So let's meet there.